So welcome back, everybody. I'm just going to jump right into the problems, and if anybody has questions, please feel free to stop me. So the first problem that you had here was to find the screw edge and mixed components of the dislocation that's in this configuration using Berger's circuits. And so, as I explained last time, what you have here are two overlapping layers of atoms. The black ones are on top, and the big white open circles are on the bottom. And just looking at this, I guess you can see pretty easily that what you have here is a dislocation that runs sort of broadly along this direction. All right, and we can see that just through the fact that you don't have black and white atoms coincident in this region, right? There's some kind of relative shift between those two atoms. So if we want to be more quantitative about it, we can draw Berger's circuits. And as I explained last time, if you're going to draw a Berger's circuit, the first thing that you have to do is define a line direction. So I'm going to analyze this segment over here first. So I define my line direction, and I defined it going to the right, but I could have also defined it going to the left. It's not I can do it either way I want. I just have to be consistent about it. And as you'll see later on, I'm going to define all my other line directions so that the direction or the sense of all these directions goes sort of broadly upward, right? So anyway, here it is. Next, what I do is I use my right hand rule. So that means that I point my thumb along that line direction and I curl my fingers, and that tells me which way the Berger's circuit should go. So what I'm going to do is I'm going to start drawing that Berger's circuit over here, and I'm going to start in the top layer, right? So this red arrow is the first part of the Berger's circuit. It starts at the black dot up here, so on the top layer. I move over to this side, and then my next arrow is going to take me downward. So you have to imagine it going into the screen. So there it is going downward. Then I'm going to go in the bottom layer up to across to the other side of the dislocation. So my next step is going to go up here, and then finally I go back up, right? So in this way I have a closed circuit. I've completely enclosed my dislocation. My goal is to redraw this circuit in a region of material that is a perfect crystal. Now, of course, I could draw a whole separate schematic containing nothing but perfect crystal, but for the purposes of this illustration, I'm just going to use this region here as my reference perfect crystal. Okay, so I'm going to start redrawing that circuit. So as before, I start out on the top. If I look carefully here, I'll see that this top arrow goes 3 nearest neighbor distances, right? So it goes from here to here, that's 1, then 2, then 3. And so I trace 3 nearest neighbor distances here as well, 1, 2, 3. Then I go down 1, and then I go up 1, 2, 3, 4 nearest neighbor distances, right? So 4 nearest neighbor distances, and then 1 increment going upward from the bottom layer to the top layer. Okay, and there's my circuit. I finished drawing it. And as you can see, it doesn't close. The starting point that I have, that I already defined for you, is here. My finishing point is also on top, but it's not at the same place as the starting point. Of course, here in this circuit, the finish and starting point are exactly the same. They have to. Here they're not. And so we're going to use the finish to start convention, which means that I'm going to draw my Berger's circuit going from the F point to the S point. Okay, that's my Berger's, sorry, not my Berger's circuit, my Berger's vector. I'm going to close that gap with a Berger's vector going from finish to start. So there's my Berger's vector. And then if I, compare that to the line direction, you can see that the line direction and the Berger's vector are perpendicular to each other. So this segment over here is an edge dislocation. All right, so that gives us part of the answer. Now let's look up here. Okay, so I'm going to define a line direction going here. Right, the line direction is always going to be tangent to the dislocation, and and as I said, I'm going to try to make it so that it always has the same sense. And as before, I'm going to use my right hand rule to define the sense of the circuit. Right, so here's my top portion of that circuit that runs along the top row of atoms. Then I'm going to go down by 1 row. then I'm going to go over by 1 atomic distance, back over to this side, and then up from the bottom back to the top. And that closes the circuit, right? So my circuit is now closed. I'm going to redraw it now in this region over here, my perfect crystal region. The number of nearest neighbors that I go along this solid line is 1, 2, 3. So I'm going to draw 3 nearest neighbor distances, 1, 2, 3. Then I go down by 1 interatomic distance, up by 1 interatomic distance, to the left by 3 interatomic distances, and then up by 1 interatomic distance. Okay? And now I have, again, a closure failure, and I'm going to close that with a vector. That vector is my Burgers vector. Okay? As you can see, it's exactly the same Burgers vector as I had before. Of course, now this Burgers vector is parallel to the line direction, so this segment here is screwed. All right? In between, and of course, I hope that by now you see that, no matter where I'm going to draw this Burgers circuit, I'm always going to get the same Burgers vector. Right? The Burgers vector is always going to be that downward pointing arrow. So if I look in this region right here, I'm also going to get the same Burgers vector, but of course my line direction is pointing this way. So my Burgers vector is neither parallel to nor perpendicular to this line direction, so this segment here is mixed. Okay? And that's it for problem 1. So any questions about problem 1? Hopefully this is rather straightforward. And I know that most of you have probably already seen Burgers circuits. But in my experience, the way it's taught, usually you don't get told that there's this importance of the sense, right? That you have to do this in conjunction with your line direction. So I hope that this clarified that.
One question is that, so if we, because for the direction that is perpendicular to the surface, that we just just put a direct step there. So if there's any differences in that direction, so can we have any way that, because this is just a planar picture, that so we have to have 3D image, right? Or say two.
Yeah, I mean, these circuits, if you're not going to look edge on to a dislocation, then you're always going to have to draw your circuits in 3D, right, rather than a 2D projection. And this is kind of a poor man's 3D image, right? Remember that you're looking at 2 planes of atoms, right? The series of black dots is the top plane, and the series of white circles is the bottom plane. So we're looking at just those 2 planes of atoms.
Okay. So in physical experiments, that we can only see the two layers of the atoms. That we cannot see the 3rd layer.
Yeah, I'm not showing the other layers, but if you're doing this Burgers circuit analysis correctly, then you should be able to draw the same circuit going into a 3rd layer or 4th layer, any number of layers. You're always going to get the same outcome, right?
Right.
In this case, the closure failure is never going to be going into the board, right? Because the Burgers vector of this particular dislocation is, not going into the board.
Okay. So one question, that's from an experimental aspect, that the atoms, even though they are the same atoms, but from the facility we see that they are like different colors. So how do we distinguish them?
The different colors here are only for the purpose of being able to visualize the 3D nature of this stacking. But I'm not trying to imply that the black dots and the white circles are different elements or different types of atoms. I mean, the only reason why they're shown differently is to indicate that they have a different z coordinate, if you will.
Okay, so if they are the same, then in reality, how do I apply this method? I mean, except for the exams, that if I'm gonna do this in reality.
You mean if you were, for example, to be given a 3D model where all the atoms are the same?
Like, I'm not an experimenter, but if I do some image, I got the image, can I use this to that image?
If you happen to have an image, for example, a TEM image that has atomic resolution, you can, draw a Burgers circuit in it. I am not aware of any any sort of tomographic method that would give you a full 3D reconstruction from an experiment on the atomic level. Now, people are getting close, right? If you look at, Atom Probe, you get 3D reconstructions on the nanometer level, but you can't really think of those as being, as giving you full sort of atomic level fidelity in the positions. So I'm not familiar with any experimental method that can give you a full 3D reconstruction of all the atoms. In a TEM image, you're likely to get just a 2D cross section.
Okay.
This kind of analysis is something that you would much more likely use in a model of some kind, right? So that could be either a computer model or a physical model of a dislocation that you would build with balls and sticks.
Okay, thank you.
Yeah.
I have a quick question.
Yep.
Can you trace the atoms that go from the top? So the first Burger's circuit, or the first circuit that you drew, the dislocation, I believe for the line at the top, you said that it goes down 3 atomic distances.
Mm-hmm. You're talking about this one now?
Yes.
Yeah. So
can you count that again? Because it seems
yeah.
like
So I'll just back up all this stuff and we'll look at just that one again. So here I am. I'm going to start at this point right there, and I'm just I want to I'm starting up here because I know that's above the dislocation, and I want to end up down here because I know that's beyond the dislocation.
Okay.
Right, and I'm going to go along the top row, and the top sort of plane of atoms here consists of all the black dots. Right, so I'm going to start at this black dot over here, and then I'm going to go to the next black dot down. So down there, this is the next black dot.
Oh.
And then the next black dot, and then the next black dot. So that's how I go, and it's 3 interatomic distances in the top layer of atoms.
Oh, okay.
Yeah, and then as I continue, this is how I'm indicating that I'm going down by 1. And if I want to return back up here, then I'm going across 4 interatomic distances in the plane of atoms on the bottom.
Oh, okay. Gotcha.
And then finally I go back up.
Thank you.
Yeah. And then when I redraw the circuit, I just count the same number of atoms, which gives me the closure field.
Mm-hmm. Gotcha. Thanks.
Okay. All right, so there we go. Let's move on to problem number 2. So here we're looking at a jog on a screw dislocation as drawn in the picture. And the idea is to show that if this dislocation moves on the glide plane, which is indicated here, and it, let's say it moves in the x direction, then the jog must climb, okay? So remember that the difference between climb and glide is that glide is motion of the dislocation within the glide plane, and climb is motion of the dislocation out of the glide plane. So to answer this question, the point is to show that the jog is going to move out of its own glide plane when the screw dislocation moves to the right. Okay, so this is the screw dislocation, right? Here it is. Here's the jog. And here the screw dislocation continues onward, but 1 atomic distance higher, right, than the first segment. And the idea is that this segment right here, as well as this segment right here, they're both going to move to the right. Okay, so in this direction. Since we're told that this is a screw dislocation, we know that the line direction and the Burger's vector must be parallel. Okay, so I'm just going to draw in a line direction and a Burger's vector. There they are. I don't know if I'm representing the sense correctly. I'm not told enough information in this problem to tell you whether those should be pointing in the same direction or in opposite directions. For the purpose of this problem, it's not going to matter. So I'm just going to draw them as pointing in the same direction. Okay. Now, when I go back over to this jog, the line direction, oh, and by the way, this, of course, right here, this arrow that I'm showing here is the normal to the glide plane, right? So I'm told that this screw dislocation is going to glide in this plane over here. right? So this is the normal to the glide plane that the screw dislocation is on. Okay, now I'm going to draw the line direction for this jog, right? And that line direction goes like that, goes downward, right? Because the jog is oriented differently. The Burgers vector, of course, has to be exactly the same because the Burgers vector is the same at every location. And then, as you'll recall, the direction perpendicular to the glide plane for that segment of the dislocation is proportional to the cross product of the Burgers vector and the line direction. Right? So the normal vector to the glide plane for the jog is pointing in the x direction. Right? It's in a different direction than the glide plane of the screw dislocation. So if that jog is going to move to the right, that means it's going to be moving perpendicular to its glide plane, which is climb. Right? So that's it. Right? You just use what you know about line directions and Burgers vectors to figure out what the normal to the glide plane is, and immediately you know that for this jog to move, it has to climb. Okay, so there are a couple of ways for that to happen in reality. One possibility, of course, is that there is diffusion, right, and mass gets transported towards or away from that jog. However, if there isn't enough time for diffusion to occur, then there are basically two alternatives. And so let me just show you that. Here I'm showing you some images from two papers. This is showing you two dislocation segments that are on parallel planes, and there's a certain resolved stress applied to them, so they're bowing out, right? And here's a little jog that connects the two, and that jog can't glide, as we just showed, right? So, the dislocations are going to bow out of that jog. And if the force acting on the jog is high enough, then eventually it may become possible for that jog to get dragged along. And as it becomes dragged along, it leaves behind point defects, in this case, vacancies. Okay, so this is, something that you can conclude immediately just from knowing the geometry of this configuration. And here are some atomic scale simulations. These are some atomistic simulations that actually show dislocations with connected with a jog being dragged along. And indeed, you see a row of vacancies being left behind when this jog gets dragged along. Now, if you happen to take that same jog and drag it in the opposite direction, you're going to leave behind a row of interstitials rather than a row of vacancies. Right? Interstitials generally have much higher formation energies than vacancies, so it's generally a lot more difficult to drag a jog in a direction that requires formation of interstitials than in a direction that requires formation of vacancies. Okay, so another option, if it's too difficult for a jog to get dragged along, another option is that this jog may actually start acting as a little pinning site, which would allow for dislocation multiplication, right? So these two bowing segments might actually, bypass each other, right? As they get longer, these two segments over here might actually bypass each other, and then you basically get these segments growing out as loops, as if being emitted from a Frank Reed source, right? So depending on how strongly locked that jog is, you can either drag it and form point defects, or you can have the remainder of the dislocation bowing around that jog. So that's what can happen as a result. And that's all I got for the homework problems. So let me stop here and see if others have questions.
I have a quick question.
Yep.
So you mentioned that the formation of the vacancies or the movement of the jog can happen by diffusion, or like dislocation climb can happen by diffusion.
Right.
And I think here you gave an example of how a stress is causing the vacancies to form.
Yeah, so if that jog is to climb,
well, like my question was quickly, the movement, the force that's applied to the material, the stress, that also can cause diffusion, is my question.
No.
Okay.
So for the jog to climb, vacancies or interstitials, mass, has to be transported to the jog, and that happens via diffusion. What I'm talking about here is what happens if there is no diffusion. Diffusion is, you can't force diffusion to occur more or less quickly, at least to first order. You can't affect the rate of diffusion by applying stresses, right? Stresses act directly on dislocations, and they can make dislocations move, but you can't make vacancies move by applying stresses, right? So vacancies are going to move at whatever rate they want to move, and that's really determined mostly by temperature. And basically what I'm saying here is, if you're not giving those vacancies enough time to move, and yet you're applying high stresses that are going to force the dislocation to move, then, in the absence of diffusion, what else can this jog do, right? Besides climb. The other things that it can do is generate point defects, or it can force the dislocation to adopt this bowed configuration. Right? So these are both things that happen only if you push on the dislocation really, really hard. Right? So you have to be able to exert a very high stress on this dislocation before you actually start generating point defects, and before you start getting these dislocations to bow past each other. But this is the sort of thing that might happen, if you're, loading your material at a very high stress and a very high strain rate. And so if you are applying a very high strain rate, then everything's in the material is moving so fast that diffusion can't keep up, right? Diffusion really plays no role in high strain rate deformation. Diffusion is too slow, basically. And yet, if you're applying these really high strain rates, then you can actually force the stresses to go really high into the GPA level. So you may, be able to force dislocations to do things that they would never do if you were applying, lower strain rates, lower stresses.
Wow. Gotcha. Thank you.
I have two questions.
Yep.
First is that I remember you mentioned the free energy for the double kink nucleation that given by argon is delta G equal to, there is a power term that is 1 minus tau over tau max.
Yeah.
So that means basically we have a criteria that tau max is required to nucleate kinks.
Right.
So I'm just
mechanically using via mechanical loading alone, because of course, the idea there is that by the time you reach tau max, there is no more activation energy to nucleate a double.
Right.
But you can still nucleate it at a lower stress. It just requires, some thermal activation.
So I'm just curious about, if we have the stress suddenly that's way beyond the tau max, does it mean that it gets harder to nucleate even? No.
I mean, at that point, at that point, you've exceeded the mechanical threshold for double kink nucleation.
Okay.
And it's just,
Okay, because from that equation, it seems that if we have a super large stress or we have super small stress, that would be equivalent for the free energy.
So you're plugging in. So I see, you're plugging in a high stress, and you're still using that expression, and you're going to say that now there's going to be a negative number under that, in that parentheses, and the negative number is going to get squared. No. That expression was developed only to come up with only to describe how the activation energy, for thermal activation of a double kink pair, varies with the applied stress. The intention there was not to imply that there is an activation energy beyond the mechanical threshold. So beyond the mechanical threshold, there's no more activation energy.
Okay, right. Okay, thank you.
Yeah.
So second question is that because the majority of the materials you are talking about are metals or some ceramics. So, but actually I'm not that familiar with this. And also, could you please comment on the framework of this crystal plasticity to some other material systems? So like, I know there's maybe not well-defined dislocations in polymers or even biological materials, but you know that metals have been studied for like a century or maybe even more. So do you have any comments of this framework of this crystal plasticity or this dislocation to some other systems?
Yeah, so in short, crystal plasticity and dislocation mechanics apply to any situation where you have crystalline order. So they have been applied to crystalline polymers. And in fact, people have developed crystal plasticity-based descriptions of texture evolution in crystalline polymers. The difference is, of course, that in crystalline polymers, because of their structure, the number of slip systems is highly restricted. So you routinely activate other deformation mechanisms besides dislocations. So not just dislocations, but also other mechanisms. I'm familiar of people with uses of dislocation mechanics in liquid crystals, right, which also support topological defects, with closure failures. So basically dislocations. And of course, one of the earliest methods of modeling dislocations was in bubble rafts. So really any kind of elastic granular packing that has crystalline order is capable in principle of supporting dislocations, and therefore is going to follow this sort of similar general principles of dislocation mechanics.
Okay, thank you. Just sorry, just one more question comes to my mind is that for the dislocations, I saw some people use FEM, some people use dislocation dynamics, some people use molecular dynamics. Do you have any like general comments on this different simulation methods, and for the particular problem maybe are more suitable, or say?
Yeah, FEM, you mean like crystal plasticity simulations?
Right. That's more phenomenologically.
Yeah. I mean, I would say that all of those simulations are intended to solve different problems, right? So atomistic simulations are usually used to investigate core structures, or dislocation reactions, perhaps nucleation, things like that. Whereas dislocation dynamics and crystal plasticity are generally used to describe, higher length scale collective phenomena such as hardening or texture evolution, or to solve boundary value problems in, for example, in polycrystalline materials.
Okay, thank you.
Okay, any other questions?
So Mike, if I can ask your discussion we just had about the jogs, can you comment on how that might change under shock conditions, if at all?
You mean the topology of this setup?
The slide 4, when you talk about jogs.
Slide 4. Well, this kind of stuff is precisely the kind of stuff that might happen under shock conditions.
Okay, good.
Right. So if you were under sort of regular low strain rate conditions, then the likelihood of jog drag is low because diffusion processes are generally fast enough to make these jogs climb. So, generation of copious quantities of point defects by jog drag is one of the phenomena that occur under relatively high strain rates and high stresses. I guess that you don't have to be at the level of shock loading to generate jogs to generate dislocations by jog drag. For example, in uniaxial tension tests, when you're approaching failure via necking, generation of a large number of point defects by jog drag is hypothesized to contribute to the nucleation and growth of voids leading up to failure by void growth and coalescence. But at that point, if you look in the neck, your strain rates might be approaching unity in a typical tension test. So, it's not the sort of thing that happens at low strain rates, but it might happen at strain rates, well below the shock level. But in shock situations, these kinds of things can definitely happen.
Okay, very good.
Small question. By any chance, do you know what molecular dynamic software the paper used to create those?
This one?
Or
I'm not sure, but if you're thinking of using molecular dynamics, certainly the easiest software to get started on and start using would be LAMMPS.
Gotcha.
Yeah. So LAMMPS is a fairly straightforward software to use for molecular dynamics simulations.
Thank you.
Hi, I have a sort of a comment. If you can comment some on geometrically necessary dislocation and statistically stored dislocations.
I
don't know whether it's a general comment, like what they are and like.
I mean that's a big discussion topic. I think I'm really just touching upon the basic mechanisms here of slip, and I think that to address some of these other issues would take us a little bit afield. So I suggest we postpone that discussion to some other opportunity.
Sure, thanks, no problem.
Okay, thank you everybody. Thank you, Mike, for your lecture and for your notes and all the discussion. And people can email Mike anytime if they have more questions and want to follow up.
Yes. Thank you very much.
Thank you very much, and we'll be back on Monday with a new lecture.
That's right. Bye-bye.
Okay, take care. Bye. Have a good weekend. Bye.